view my screen. Am I audible to all of you?
Yes, sir, audible.
Okay. So we started some introduction of ARM architecture, and Professor Niranjan will continue the architecture in more depth. We will in between, I request other students to mute your microphone so that it will not create any disturbance. If you have any questions, you can unmute your mic and ask. But if you do not have any questions, please mute your microphone. Because it will be very difficult to switch me between different windows to mute all of you. It's very difficult for me, right? So in last lecture we discussed about why we use assembly language, even though it is a complex, even though it is difficult to learn and it is difficult to program, though we are using it because it provides us faster execution. It needs less program memory, as we have seen that whatever the hex file generated with help of assembly language program, and that hex file is having a comparatively, it occupies less memory compared to the C program, and assembly language is very much near to the hardware, and that's why we go for it, right? We have also seen that AVR instruction set, we have a total about 118 instructions. There was a questions from WhatsApp group that whether we should use AVR Studio or whether we should use Microchip Studio. In that case, I will tell you that initially, Atmel company was producing the AVR. So there was Atmel Studio. Later on, it was AVR Studio. But now that Atmel company, Microchip has purchased. So now Microchip is manufacturing both microcontroller, AVR microcontroller as well as PIC microcontroller. Originally, Microchip was producing only PIC chip, but now it has occupied that Atmel company also. So nowadays, Microchip is producing AVR microcontroller also. So they have done some modifications and given a new software called Microchip Studio. So you can also use Microchip Studio to program the AVR microcontroller. The advantage of using Microchip Studio is that you will be able to program AVR and PIC both using the same software. So either you can go for AVR Studio or Atmel Studio or Microchip Studio to program the AVR chip. Not an issue, right? Almost in all the softwares, the way of working is same. We have seen last time the types of instructions, and we will discuss all these instructions one by one. We have also looked at hex file format. So last time I have shown with one example, we assembled one program, assembly language program, generated the hex file, and we try to interpret that hex file. So in that hex file, basically there are different, always that hex file will start with a colon. So always it starts with this colon. Okay, is this my slide visible to all of you? Is there any issue, or it
Yes,
is
sir,
visible?
visible.
It is visible.
Yes, sir.
Okay, good. So this colon, it will always start with that. So initial this 02 says that in this line only, two codes are there. So ultimately, this AAA will provide you address from which address your code will start. So 000 is the address from where the code is starting. TT says that what is there in that particular line, right? And then at last there will be a checksum byte. So this hex file we produced last time, and I have shown you the typical example. Now let's look at this instruction. LDI R16, 0x55. This is one instruction. This instruction, what it will do, it will transfer the data 0x55 to register R16. That means we try to load some value into register R16 with help of this instruction. So this immediate value 0x, now here x means it is a hex value. if you want to transfer the decimal value, simply you can remove this 0x here. If you simply write LDI R16 comma 55, then only 55 decimal value will transfer to the R16. In this case, whenever we write 0x, that means hexadecimal value we are transferring to the register R16. If this instruction is assembled and a hex file will be generated, then 16-bit opcode corresponding to this instruction will be 0xE505. So if this E you convert into binary pattern, it is a 1110. This 5 means 0101. This 0 means 000, and this 5 means 0101. So this binary pattern, 16-bit binary pattern, will be generated by this assembly language instruction. As I told you, this is the job of assembler. Assembler will take this instruction as an input and it will produce this bit pattern as an output. So this is called machine code. This is nothing but a machine code. This is our assembly code. Why machine code is required? Because microcontroller or microprocessor will not understand this assembly language instruction. Microprocessor and microcontroller will be able to understand this type of a bit pattern if you have. But for a human being, it is very difficult. If different types of a bit patterns is given to you, it will be very difficult for you to understand this bit pattern. So for us, it is very easy to understand this type of instruction, LDI R16 0x55. If it is written, you will immediately tell that load immediately 0x55 to R16, right? Can anyone tell me if I want to transfer some data 0x66 to R17, how you will write the instruction?
सर क्वेश्चन रिपीट कीजिए तो.
Okay. What I will do, I will open the Word file and then I will ask the question there only, so that it will be very much clear to you, right? I want to transfer data 0x66 to R17 register. So what should be our instruction? See, we have given like this, LDI R16 comma 0x55 means this instruction will transfer data 0x55 to register R16. Now my question is that what should be the assembly language instruction to transfer 0x66 to R17?
LDI R17 comma 0x66
comma 0x66. Perfect. You are right. Right. So it is very easy for us to understand this LDI R16 comma 0x66. This we are actually writing to transfer 0x66 to the R17. But now if you look at this, it is very difficult for us to write in this way and to understand in this way, right? So in this case, these 4 red bits 1110, this will distinguish that this is the LDI instruction. So this 1110, it is corresponding to this LDI instruction. So if I say that LDI, whenever I am saying LDI, my microcontroller assembler will transfer it to this bit pattern 1110. Then after, whenever this blue digits, this 000, it indicates that register R16 is the first operand. So that means if I write it here, that if my register is R16, then it will be represented by 000, right? And whatever the written in a green is a data. This is 0101 is a green, that is related to 5. This 0101 is also a 5. So this both is for this data 0x55. So now in our new case, if we want to do the same thing for this instruction, if we want to find out what will be the bit pattern corresponding to this instruction, that means our first 1110 will remain same because it is a still LDI instruction. Then after instead of, in this case our bit pattern was something like this. Just I will copy and paste it here so that you will get the idea. Our bit pattern for this instruction was this. Right. Now we are trying to write the bit pattern for this instruction. Now in this case the first bit pattern will remain same because instruction is still LDI. Next will be 010 will be replaced by another new data because now we have a 2 digit 66. So this will be 0110. And then 000 is corresponding to R16. So for corresponding to R70 it will be a 0001. And then after another, in this case another 5 is there, in this case there will be another 6. So our bit pattern for this instruction will be this, right? And our hex code corresponding to this instruction, in that way it will be a 0x E6, let me write in capital, E6 and 16. Right, so for this instruction, the code generated was 0x E505. But for this instruction, code generated is 0E616. And corresponding bit pattern generated is this. So, as a human being, we can understand this instruction that we are going to transfer 66 to R17. But our microcontroller and microprocessor will not understand this. It will understand only this machine code. So we can say this is a assembly language instruction and this is a machine language instruction for the microcontroller and microprocessor.
સર મશીન લેંગ્વેજમાં વચારેના બે પાર્ટ છે ને 0110 અને 0001 વાળા એ રિપીટ કરો ને.
Okay. Let me come back to this slide and then again I will repeat it. Okay. This is actually our instruction and this is how we are converting that into bit pattern. But don't worry, we have not to do this process manually. Our assembler will do this task for us. So our AVR Studio, Atmel Studio or a Microchip Studio will do this task for us. So whenever we write the instruction in assembly language, that assembler will convert that into machine language. So I will repeat this again. This 1110 is corresponding to LDI. Let me open the pointer again. Okay, so this R16 LDI is corresponding to this 1110. This 000 is corresponding to R16. This 5 is corresponding to this 0101. This another 5 is corresponding to the 0101. So at every instruction, if I am changing this data here, instead of 0x55, if I am writing here 0x12, then this will be binary code corresponding to 1. This will be binary code corresponding to 2. So if I am changing this data here, then whatever the digits or binary digits are written in a green color will change. This two will remain same because we are performing job with a R16 and we are performing job of a loading some data to the register. So whenever we use LDI, originally it will start from this 1110 which is written in a red color. And this 000 which is written in a blue color, this represents the register. So these 4 red bits are corresponding to LDI instruction. 4 blue digits are corresponding to the R16 and 8 green bits are corresponding to the data. Is it clear?
Yes, sir.
Okay, sir.
It is clear. Okay. Now if I am changing this register here, then this bit combination will change. So for example, if I am taking here R23, then that bit combination will be 1110. Now let me write all these bit combinations here. Let me write it here in a word file so that it will be very much clear to you. Okay. So that means the bit combination corresponding to R16 would be 000, R17 would be 0001, R18 would be 0010, R19. So it is in sequence, right? 0011, R20, 0100, R21, 0101, R22, 0110, R23, 0111, R24, 100, R25, 1001, and so on. I will not write all the combinations here, and so on. I can go up to R31. R31 means 111. So you can specify only with the instruction LDI R16 0x55. I can write it in this way. But if I write in this way LDI R0, 0x55, this is invalid instruction. Why it is invalid instruction? Because there are no bit combination corresponding to R0. We have bit combinations available only for R16 to R31. Because only we have a 4 bits available to specify the register. So if we have a 4 bits, 2:4. 2:4, that is equal to 16. So only 16 registers we can specify. But in AVR microcontroller, we have a 32 registers. So we have to decide which register we want to work with for LDI instruction. So the AVR architecture, designer has decided that let us use R16 to R31 with the LDI instruction. So, if you write LDI R0, something, then that will be your invalid instruction. You will not be able to write R0 to R15 here. You have to write from R16 to R31. Why? Because we have only 4 bits to represent the register. We do not have a 5 bits. Then some of you may ask that what will happen if I use 5 bits to represent the register, right? Instead of these, if I represent register with a 5 bit, what will happen? Instead of 16 bit, our code will become 17 bit. But we have decided in our architecture that every instruction will be having a length of 16 bit. So we cannot increase more than 16 bit, right? Otherwise, at least for a 1 bit, you have to occupy one more byte, entire byte, and ultimately your memory will increase. So there is a trade-off. We want to save the memory also. We want assembly language instruction in such a way that your hex file should have a less number of bits. So now here there is a limitation. We cannot specify along with the LDI instruction. We cannot specify R0 to R15, but we can specify from R16 to R31. Is it clear to all?
Yes,
Sir,
sir.
why it is starting from 16 only R16?
Okay. Yes, very good question. I was expecting this question. Designer must have thought that initial registers will be used in many places, because whenever you want to start, you will start with R0 R1 from initial registers only. Even professors, if you look at in a physical classroom, whenever professors are teaching, normally they will look at initial 4 or 5 benches. They will not look mostly at the last benches. Of course, it is not true for me. I am looking at all benches. So initially, designer thought that R0, R1, R2 are the initial registers and will be used for many operations. nobody will touch to this R16 to R31. So let us start it from R16, and that's why that could be this is actually my guess, may not be true, but I didn't find this answer from anywhere. So this is my own interpretation, and that's why designer must have thought that let us start from R16. Okay.
Okay, sir.
So now this is similarly one more instruction called add addition instruction. So addition instruction is very simple. Add R23, R11. So in this case, now again you require 4 bits or some more number of bits to represent this add instruction, right? And then few bits for R23 and few bits for R11. Fortunately, we do not have a 16-bit data here, so we have to only allocate bits for addition instruction, bits for R23, and bits for some other register. So we have to allocate bits for 2 registers and 1 instruction. We have 16-bit available. So what we are doing here, out of 16, we allocate these red bits corresponding to the instruction. So this 6th bit will represent the instruction add. So these 6 red bits will distinguish this instruction as the addition instruction. Then these 5 bits which are shown in a blue color are dedicated for 23 register, and this green color will represent another register R11. So now we have a flexibility here. We have a 5 bits available. 5 bits available, so you will be able to represent 2:5 means how many registers you will be able to represent? 2:5 means
32.
32. That means now we have a flexibility. We will be able to represent all 32 registers from R0 to R31. So with add